everyone, and welcome to today's webinar, Coupling TAITherm and OpenFOAM for Automotive Applications. My name is Chris Niva, Marketing Operations Coordinator at ThermoAnalytics and host of today's webinar. Our presenters today are Francois, Sasha, and Kamesh. Francois is the Head of Business Development for the EU and has been a part of the TAI family since 2014. He received his Master's of Science in Automotive Engineering from Cranfield University, and his current focus is business development and automotive thermal management applications. Sasha joined the TAI family in 2019 and has over 15 years of experience with thermal and CFD simulations, mainly in the automotive industry. He received his Master's of Science in Aerospace Engineering from the Technical University of Delft. Kamesh joined the TAI family in 2018 and is our Business Development Manager, where he helps formulate new business strategies and support customer relationships in Europe and Asia. He received his Master's of Science in Mechanical Engineering from RWTH Aachen University, MBA from Gizmo Business School, and has worked with TAITherm and our team for over a decade as a loyal customer during his time at Audi and Volkswagen. Throughout this presentation, you may submit questions in the question box and we will review them at the end. We are also recording this webinar and we'll be sending you the link following this presentation. With that, Francois, if you're ready, you may begin.
Okay, yes, thank you, Chris, for the introduction. Hi, everyone. Thanks a lot for joining us. Today, we will be talking about the coupling between TAITherm and OpenFOAM for automotive applications. So a quick overview. Our agenda will be the following. So a quick introduction, a few words on the coupling processes we are using, a showcasing of different automotive thermal management applications, a chapter on advanced process customization, and finally a conclusion. So on to the introduction. So as a background, I'm showing here the typical applications us automotive engineers face in terms of thermal management. So it usually revolves around safety, like looking, for example, in the underhood compartment, that there is no overheating after a soak, looking at brakes, that you don't have your brake fluid boiling, but also looking at durability applications, like, for example, an exhaust manifold when you do multiple starts and stops, a battery when you do fast charging, component into your cabin when you do solar loading. The vehicle will soak in the sun, and that will definitely cause some damage. Other applications include thermal comfort when using a human model to simulate the thermal comfort inside the car. And other applications revolve around performance. So, for example, performance of the HVAC system to cool down the system, the cabin, or the defrosting system of your car. So these are just some typical applications we are faced with. And at TAI, we have a number of tools to work on those. So as you may know, we have TAITherm, our main product, a 3D thermal solver. We have a number of dedicated extensions for specific physics, such as the exhaust, the battery, or the human model. And we have an external tool called CoTherm for coupling and automation. CoTherm also has its own extension called Drive Cycle, which is there to do simulations of long duty cycles. So typically for coupling TAITherm with other tools, we have different solutions. This usually arises when there is a need for multiphysics simulation. So adding some physics to your thermal simulation or adding thermal results to your simulation in a third-party tool. So there are mechanisms to exchange data between TAITherm and other tools such as system tools, CFD tools, electrical networks tools, or structural tools. TAI has developed a tool for this named CoTherm. So if you've never come across CoTherm, this is typically what it looks like. It's a tool where the engineer can graphically design a process which is made of tasks such as running a command, like starting a tool or stopping it or whatever, making a decision like, should I continue to iterate on a certain tool, or should I stop and go to the next time step, or such things. Import, export data, should I send data to the third-party tool? Update data, like if you're coupling with CFD, should I update all my heat transfer coefficients that are coming from the third-party tool? Message, should I display a message or a log file or something? So these are typically the tasks you would find in this, what we call canvas, which defines your process. And it's using a number of resources. So those can be files, tools, selections. We also have variables that can be displayed here as monitors. So if you have a simulation running, you can monitor in real time the different variables of your process, the different results, the convergence criteria, and so on. We have a console view of the different things that's happening if you are running different tools. So this is typically what CoTherm would look like. So in a nutshell, it's a tool to couple multiple third-party tools through visual scripting. And one of the strengths is you can do real-time monitoring. So if you're running on an HPC, that's quite a powerful feature. And it also has additional features such as sub-processes. So you can have a process nested into another process. You can have parallel tasks if you're running, say, multiple CFD jobs at the same time. It has Python journal capabilities. It can run macros from external tools. It can scan your CFD model when you need to select which surfaces should be coupled between them. And it has its own optimization tool. We support, obviously, a number of tools such as StarCCM+, Fluent, OpenFOAM, and so on. And other tools are coming, and any tool in the end can be coupled with the addition of additional scripts. But today we will be talking about the coupling between TAITherm and OpenFOAM. So this relies on our usual coupling paradigm where TAITherm is sending temperatures to OpenFOAM, and OpenFOAM is sending back heat transfer coefficient and free temperature to TAITherm. We have a number of readily available coupling processes for the different applications we described before. So like steady to steady, if you are simulating a steady state event like a car cruising at a steady speed, but also more complex coupling strategies for transient simulations, like if you're doing a heat soak or a cabin pull down. We'll have more examples of this in the next section that Sasha will present. I'll hand it over to you, Sasha.
Thank you, Francois. I will show some thermal management examples. Starting with Underhood thermal protection. So here you see the coupling between TAITherm and OpenFOAM. On the top, the TAITherm model, and on the bottom, the OpenFOAM. So TAITherm is calculating the surface temperatures, mapping them on an element base to OpenFOAM. OpenFOAM updates the convection. HTC is fluid, maps them back to TAITherm. So this coupling process is shown here in CoTherm. In the template, you see the run thermal, run CFD. And we keep iterating this until all the temperatures in the Underhood are stabilized. Um, the OpenFOAM setup is what you see here for the geometry. We have a very detailed underhood, and which is meshed in snappy hex mesh, which is basically a wrapper that comes with OpenFOAM. It's meshed on a 64 gigabyte machine. Took about 12 hours, and we have a very fine underhood cell size of about 5 millimeter. The geometry for TAITherm was exported directly from Snappy Hex Mesh. You see it here, again, very detailed with a lot of PIDs, and has about 3.5 million elements. So the OpenFOAM setup, we're simulating a mountain uphill towing case, so low vehicle speed of 35 km per hour, MRF on the fan and the wheels. The porous media have a heat release, and it's a steady state simulation with a K epsilon turbulence model. In TAITherm, we're using the exhaust module. And the runtime for this coupled simulation with multiple couplings was about 24 hours on 20 processors. Here you see the surface temperatures that are coming from the coupled run. You see the exhaust, which has very high temperatures. And you can look at the surface temperature of the surrounding components. Make sure they don't overheat. You can look at the flow field and try to optimize the flow around the components or upgrade the materials, add heat shields. And then in addition, in TAITherm, you can look at where the heat is coming from. So for example, for this point here on this pipe, you can look at where most of the radiation is coming from. So it's mainly coming from the manifold, but you see there's also a lot of heat coming from the turbo. So you can take that into consideration when you're designing a heat shield. And in addition, you can look at which is the most dominant heat source. So here you see that this point is mainly receiving a lot of radiation, but it's also cooled by convection, and there's a little bit of conduction to the surrounding. The next example is brake cooling. So again, here we're coupling the TAITherm model with the OpenFOAM model. The OpenFOAM geometry, we're using a symmetry plane, again meshed in snappy hex mesh. We're using a very fine mesh around the brake disc of say about 1 millimeter. And furthermore, we have local refinements. So here you see a brake duct. We have a local refinement around the grill. The TAITherm geometry is shown here. It is a volume meshed to represent the conduction accurately. So you see the heat from the brake disc goes to the rim and the axle. So simulation setup, we have the brake duct. We're running 100 km per hour, MRF on the brake and the wheels. It's again steady state with the K epsilon turbulence model. And this coupled run steady state takes about 22 hours on 20 processors. So then you can look at the flow field. You see here the flow going through the brake duct aimed at the braking system. You can look at surface temperature and the HTCs on the surface. So where is the flow going to? And then you can try to optimize this flow and have the most efficient cooling. From that coupled run, you can do a brake cycle in TAITherm standalone. So you would import the HTCs from the previous steady state run as a function of time. linearly interpolated with vehicle speed. You import the brake power as a function of time, and then you can do this drive cycle, where we're braking from 100 km/h to 0 in about 5 seconds and accelerate from 0 to 100 in 25 seconds. You can repeat this 20 times, and then you see that the brake temperatures are going up. And then you can make sure that the brake temperature doesn't overheat and doesn't go above the critical temperature where it could start deforming. And in the same time, you can look at the brake oil temperature because you don't want that to start boiling. The next example is cabin cooling, presented in a paper by Dennis Hinz. Showing here pseudo-transient coupling. We're simulating a 30-minute cool down. And for this, means that we're coupling at different instances. So at different times, we are coupling with OpenFOAM. Here we see the OpenFOAM volume mesh that was used for the simulation. And then we're going to simulate the cool down of a hot cabin. So it's a hot soak, the vehicle positioned in Phoenix, Arizona on a hot day. So then when the human is entering the vehicle, it's very warm, very uncomfortable. Then you switch on the heat, the HVAC, and we simulated 30 minutes cool down. Here we see the imported convection from OpenFOAM at different instances. 1 minute, 50 minutes, 30 minutes, we have multiple points. You see that the fluid temperatures are cooling down over time. And then you can look at the surface temperature over the cool down. The surface temperatures cooling down during 30 minutes. And in addition, you can look at the human comfort. So whether the driver is feeling comfortable or not. We look at sensation. This means, is he feeling very hot or very cold? And is he comfortable? So when the driver enters the vehicle, at the beginning he is very hot and therefore very uncomfortable. So looking at this component for the face. But then with the HVAC on, the temperature is starting to go down and he's starting to feel more comfortable. But then over many minutes, since the HVAC keeps working, he's starting to feel more cold and more uncomfortable. Then the last example of battery cooling, getting more and more important in the automotive industry. We have coupled this battery pack that you see here with OpenFOAM. And in OpenFOAM, we are only coupling the cooling channels in the cooling plate. So that's a very small simulation, goes very quick. We do a steady state run there to obtain the heat transfer coefficients. And then we can simulate this battery pack. We have 48 cells, prismatic batteries, 4 in parallel, 12 in series. And we're simulating this with our electrical model, the NTG equivalent circuit. So with this, we can really simulate the charge and discharge of the battery pack. Look at how full and empty the battery is. Good, we have a cooling plate underneath with U-shaped liquid channels. So you see that we're using here fluid streams, which we will combine with the HTCs obtained from OpenFOAM. So we import the HTCs and then we do the TAITherm standalone that we can run quickly for this drive cycle. It's a 24-hour drive cycle starting at 8 a.m. This is the current over time, meaning driving during the day, charging at night, 24 hours. The coolant mass flow is changing over time. It can be any curve. Here it was chosen to be cooling during driving. The ambient temperature is changing. and then we can look at the temperature results. So this drive cycle of 24 hours, you see that the battery starts full 100%, but then during the drive cycle, at the end of the day, it's at empty %, then being charged again. You see the cooling channels that are, as a function of time, cooling with the imported HTCs from CFD. This is hours, so we're about 4 or 5 hours. And then at peak times, you see that the battery temperatures are heating up, and that you start to see a lot of those temperature gradients on the top and in the rear. And that's exactly what you want to avoid, because such temperature gradients, they impact the lifetime of the batteries. So you want to make sure that the temperatures are as uniform as possible. And a drive cycle like this takes about 2 hours on a simple laptop. All right, I will now hand it over to Kamesh, who will present advanced process customization.
Thank you, Sasha. Till now, we have seen some aspects of the CoTherm process and some practical applications in automotive industry, TAITherm coupled with OpenFOAM. And in the next few minutes, I'm going to walk you through some advanced capabilities of CoTherm to customize, automate, and do both of them. I'm trying to click. Right. Sorry, some technical. Oops. Okay. Sorry, trying to get to the slide. Oops. Didn't do a short try. Okay, right. Sorry about this. I'm going to demonstrate with an example. At first, I'm going to show, with reference to thermal model, how to create the mesh in OpenFOAM and do the OpenFOAM setup and run the solution, everything automatically. Later, I saw some kind of advanced customization, how to do surface mesh refinements based on user inputs from TAITherm graphical interface. Later, I'm going to show some additional scope for customization. I want to go to the next slide. Right. Right. So here, the canvas, what you see on the left side, it has the whole process integrated into that. So basically, it will define what kind of simulation strategy you're using, what kind of methodology, how to couple if you want to run the TAITherm in completely transient run or in steady state. Similarly, what is the kind of coupling strategy used for CFD, how often you run, how often you couple, and things like that. The whole method is integrated into the CoTherm canvas into different blocks. Every block has a functionality, and it do something in the process. So there is a lot of information exchange between different blocks. They interact and exchange the data. For example, to exchange the temperature from TAITherm to the CFD and import the convection, or update a convergence loops if it reached convergence, or it plots some kind of data, etc. In short, the whole complexity of the method is integrated into this canvas. Depending on the kind of application, there are different kind of templates developed by us, and you can use them. As an example, as a simple steady state solution, what you see on the right side top. So TAITherm will run, exchange the send the temperature to the CFD, and CFD take that as a boundary condition and give back the convection, and this runs on and on till it reaches the convergence. For the real-time transient scenarios, it could be a soak followed by cool down, or running a car on an autobahn or a highway and park it. Then there is a kind of transient thermal field. The heavy mass components take some time to lose the heat. To analyze such things, or any drive cycle scenarios like WLTPs or stop and go scenarios, or braking, or battery charging and discharging, or any kind of real-time transient cycles, there is a template to capture all this physics, and it is incorporated into the CoTherm canvas. I'm going to speak in the next slide about the mesh flow geometry. If you see as a sub-process, which is in blue color here, if you go to that, it is a little slow, sorry. Yeah, fundamentally, the reason why we choose this is, like, you know from your experience, it often takes a lot of time to create the CFD mesh, CFD models, and run it. So what the motivation behind this is, like, automatically running and generating a CFD mesh and running that from a thermal model. If you see my mouse on the right side, you see a kind of pipe here, which is a simple representation of exhaust system, and some boxes around that. That could be heat shields or the floor panel or whatever it is. The CoTherm, the canvas, when it will automatically create the file structure for OpenFOAM, for system files, constant, like some kind of parameters like block mesh disk, snappy mesh disk. It creates the structure. On the top of that, it creates a tunnel around this thermal model where the flow goes, for example, in this case, from left to right, and exchange with information with the thermal model, in this case from TAITherm, and create the mesh automatically. And like you have seen in the other slide, from there it goes to the running the TAITherm and running the CFD, and it goes on and on. This is an example, and if you see on my mouse on the left side, this can be additionally customized. I'm just waiting. My slide goes to next. Right. Here you see the two CoTherm blocks, get parameters and add refinements. Fundamentally, it is reading the TAITherm file. In the TAITherm file, there are like parts, assemblies, and things like that. We are taking an advantage of assembly name. In this case, it's RFI assembly. So the user goes to this assembly, create a new assembly out of a few part names here, in this case, pipe, front and back of the pipe, and create an assembly. And the convention here is RF5, which is refinement level of 5, and in other case, it's 6, 7, and 4. The CoTherm blocks will automatically read these assembly names and know for which part names, and it creates the SnappyX mesh dictionaries with regions and block and with levels. Fundamentally, it creates the structure for this, and the result will be just waiting for the slide to go on. Right, it creates automatically the mesh, and if you see, for example, here for the pipe assembly, it has automatically created 5 levels of refinement, and if you see from bottom to top, the refinement level goes one step up. Such things can be nicely automated. I will show you this in an action. Basically, you see here, I hope it's running. Right. So once this mesh process goes in, you see the blocks here. On the left side, there are some kind of inputs which is needed for this whole process. And if you go up, and yeah, if you just press run, it goes to the mesh process, and it creates all this kind of refinement blocks inside that. So I want to open a TAITherm model. This is to demonstrate you where the assembly is, how to create that. And if you go back, once the mesh, SnappyX mesh is running now on the bottom, and now it runs the CFD, the one in the blue color lines, the green color one. And then once the CFD is running, it goes, it checks the convergence and see if the thermal goes to the thermal side. Once the thermal is running, if you see on the right side here, the monitors will be updated. And you can see the convergence and see which parts are converged and things like that. And this method, what I've shown, is a simple thing, but you can extend it to different kind of OpenFOAM parameters, like it could be boundary layer refinement, or it could be volume mesh controls, etc. On the top of that, so you can add an additional physics in a CoTherm block. It could be, for example, you can create your electromagnetism physics for an e-motor and put it in a CoTherm block and run it. So you have all the infrastructure around it, so you don't need to worry about how it interacts with it. Just put in the CoTherm block and it will run. On the top of it, if you want to add some controls, like for HVAC controls, using GT, for example, or for Simulink or any other software, you can integrate it quite easily. And it is the coupling is not limited to OpenFOAM itself. You can run to any tools, any commercial CFD code, or any kind of FE tools. There is no limitation there. On the top of that, most important thing is you can also optimize using CoTherm. CoTherm comes with some basic algorithms for optimization. As an example, if you take a cabin, you can optimize the energy consumption inside the cabin using the radiant panels, the seat heating or steer wheels heating, etc., and try to find a cost function which tries to find the best optimum way to get passenger comfort. With that, just trying to go to the next slide. Right, I come to conclusions. ThermoAnalytics provides a robust and very easy coupling process in terms of CoTherm canvas. You can couple TAITherm and OpenFOAM. With the CoTherm, you can get the templates from the CoTherm for different applications, like what you've seen in the presentation today. The advantage of this is, like, you don't need to do a lot of scripting, a lot of programming, which may be a lot of error prone. With CoTherm, you get well-tested methodology as a CoTherm canvas. You need to slightly adjust to your cluster and hardware requirements, but then it's good to go. You just plug in thermal model, CFD models, and it will be running. And last, you can do advanced customization. You can do automation. You can do your life very easy and less error prone. Yeah, with this, would like to thank you everyone for attending this webinar, and we are open for some questions.
Yes, thanks, Kamesh, Francois, Sasha. So here we go. Can you also do momentum freeze with OpenFOAM simulation for cabin?
That is a possibility. So it's a capability in OpenFOAM, and we can couple with that. So especially for cabin simulations, this speeds up your simulation significantly and allows transient simulations.
Okay, here's another one. Are there coupling templates available with CoTherm?
Oh, that's a great question. Yeah, we have quite some coupling templates for different applications. Yeah, user can take advantage of that and yeah, run them. There are a lot of them are available.
Okay. What is the communication with OpenFOAM file-based?
Yes, the communication of surface temperatures and convection, HCC, and fluid is done on an element level, and yeah, this is done through text file mapping, but a neutral file export is also possible.
Okay. Can we only realistically render the OpenFOAM results, or can we also render the TAITherm results?
You can do both. So both the results from OpenFOAM as well as the surface temperatures from TAITherm can be exported and rendered.
Okay. What is the language needed to modify the templates to couple with OpenFOAM?
Go ahead, Kamesh.
Right. There are multiple ways. You can use Python. Python, I think, is the greatest way. There is also it also comes with CoTherm. There are some CoTherm kind of language inside that, but mainly you can use Python for doing that.
All right. To which OpenFOAM versions can we couple?
We can couple to most open source and commercial OpenFOAM versions.
Okay, looks like that's all the questions that we got. So that will complete. Oh, actually, hang on, we got one more. In your cooling channel example, you used fluid streams to model the coolant, but HTCs from CFD. How much different would TAITherm computed HTCs be in comparison?
Oh, very good question. So for the quite simple channels that were presented, TAITherm can represent the flow inside the channels quite well. So that would be very similar. But you can also have very complex channels with a lot of flow splitting or separations, and then people prefer to have a bit more accurate input from CFD, and that's what's possible. So you import your HTCs, but then you linearly vary them with, for example, mass flow, or with your Reynolds number, so that you only need to do one coupled run, and you can do your 24-hour transient in TAITherm.
Okay, and had another one come in. Do you help people to install OpenFOAM, or is it assumed that it's already installed?
We can fully support that.
All right. Well, that will complete today's webinar. Thank you everyone for attending. You'll receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. If you have any more questions, please do not hesitate to reach out to us. Thank you everyone for attending, and have a nice day.